everyone, welcome back to this week's algebraic graph theory seminar. This week, Robert Bailey, he's going to talk about distance regular graphs with primitive automorphism groups.
Okay, so thank you to Tina and the organizers. Thanks especially to Sabrina for the invitation. So I'm going to be talking about distance regular graphs with primitive automorphism groups. So I'm from the Grenfell campus of Memorial University, which some of you have probably never heard of. In case you're wondering what that is, we're in Newfoundland, in the city of Corner Brook, which is on the west coast of the island of Newfoundland, a long way from St. John's, where the main Memorial University campus is. Okay, so that's where I am usually, but right now I'm actually on sabbatical and I'm in the city of Rijeka in Croatia. In case you're wondering where that is, here's a map. And it's a very nice place to visit. In fact, I would encourage you to actually come here and experience it for yourselves, because in a few months' time, in July this year, the combinatorics group here is organizing what's called the Rijeka Conference on Combinatorial Objects and Their Applications. Apologies to any Italians. We know that's not how you spell ricotta cheese, but that's what the abbreviation works out as. And there's be a number of interesting speakers, and there's a website which I can share with you later on if anybody's interested, but registration for that is now open. So if anybody's interested in coming to Rijeka this coming summer, then I'm sure you'd be welcome. Okay, so what I'm going to talk about today is joint work with two of my undergraduate research students from the summer of last year and also the summer of the year before. You can tell from the picture that this was during COVID, excuse me, and they were working in this project, cataloging distance regular graphs arising from primitive permutation groups. I'm going to explain all of that. Now, this talk is about groups and graphs simultaneously. So when you are working with both of these objects at the same time, you have to decide which one is going to be called G. And so apologies to any graph theorists, G in this talk will always denote a group, and graphs will be denoted by gamma. And all the groups and all the graphs that we'll talk about are going to be finite, which it's pretty common for this kind of work. Last week I gave a version of this talk to an audience largely of group theorists, so to be a little more cautious about that then. Okay, so to start with, what kind of graphs are we talking about? Well, distance regular graphs. And you can see from the list of participants that most people will know this already, but just so we know where we stand. So gamma is a finite graph, and I'm going to let the distance between two vertices be noted by d of v and w. And so what I'm going to do is fix a vertex v, and then break the graph up into layers, sort of at each possible distance from that vertex v. So gamma 1 of v is the neighbors of v, gamma 2 is those at distance 2, and so on. And so for any graph and for any vertex, provided the graph is connected, you can always make this partitions of the vertices. And so what I'm going to do now is pick another vertex w in layer I, so at distance I from v. And what we can do is then count the number of neighbors of w relative to what the distance is from v. So ci denotes the number of vertices adjacent to w that are one step closer to v. Ai is the number of neighbors of W at the same distance I from V, and BI, the number of neighbors of W at distance sort of one further away from V, so distance I plus one. So you think of CI, or C as denoting closer and B denoting beyond, if you're trying to remember which is which. And we can do this counting in any graph, starting from any vertex V and any vertex W in the ith layer. But in general, this will depend on which vertex V you chose as the root and which vertex W you pick in that ith layer. What makes a graph distance regular is that these numbers depend only on this distance I and not on the choice of V and W. So it doesn't matter which vertex we start from. And once we've chosen something, once we're in the ith layer, it doesn't matter which vertex in that layer we pick, these numbers will always be constant. So that's what makes a graph distance regular. So a couple of important special cases. If the diameter is 2, we get strongly regular graphs. And if we have, bringing the group into it, if we have a graph where the automorphism group is acting transitively on the pairs of vertices at each distance, so if you pick 2 vertices at distance I, pick another 2 at the same distance, there's some symmetry of the graph which moves one pair onto the other, and it does this for each distance, then you have a graph which is distance transitive. Distance transitive graphs are distance regular. In fact, the history of this is distance transitive graphs were invented first, and then it was observed that they have to have these regularity properties, and then distance regular graphs arose as, what do we get if we assume just the regularity properties and without wondering if there's a group involved. Okay, so we can put these parameters into an array, which is called the intersection array of the graph. The little stars indicate the 2 which are not defined, because you can't have a vertex beyond the last layer or before sort of layer 0. And there's certain observations that you can make for any distance regular graph. It has to have valency k, which works out as being b0, the number of neighbors of the root vertex. You can't, A0 has to always be 0 because there's only that one vertex in layer 0. And for the same reason, C1 has to be 1. And also because the graph is k regular, you have that total number of neighbors of a vertex in layer I has to add up to k. So each of these columns must sum to k. And that last observation means that the middle row is kind of redundant information. So if you want to express the intersection array a little more succinctly on a single line, you can do it like this. So why do we care about intersection arrays? Well, they encode a lot of information about the graph. And one key observation, which is used to rule out a lot of potential intersection arrays from whether they can correspond to a graph or not, is that you can deduce from the intersection array the entire spectrum of the adjacency matrix. The way this works is you take those 3 rows and put them as the diagonals of a d+1 by d+1 tridiagonal matrix. That ends up having d+1 distinct eigenvalues, which turn out to be the distinct eigenvalues of your graph, your distance regular graph gamma. And you can also, there are formulas for implicitly deducing the multiplicities of those eigenvalues from the intersection array as well. And that's just sort of one thing you can encode in the intersection array. Just a piece of notation for you, in the case of strongly regular graphs, so these are usually defined as having n vertices, valency k. Any 2 adjacent vertices have lambda common neighbors. Well, that means that A1 has to be equal to lambda. Any 2 non-adjacent vertices must have mu common neighbors. Well, that works out as the number of neighbors of a vertex in the second layer, the number of neighbors in the first layer, so that's C2. So you can, if you have a strongly regular graph, you can move between these 2 notations, but perhaps the nk lambda mu notation is a bit more well known in that case. So we will see that later on. So here's a nice example, distance regular graph of diameter 3. It's the cube, has 8 vertices. Each vertex has valency 3. And so if you pick a vertex in layer 2, so that's the second column of 3 vertices, each vertex has 3 neighbors, 2 of which are in the previous layer, 1 is in the subsequent layer, and there are none in the same layer. So that's the 2, 0, 1 column we have there. The fact that the middle row is all zeros is because the graph is bipartite. So this is an example of the kind of information you can deduce from the intersection array. An all zero middle row indicates a bipartite distance regular graph. So that's just a hint of the kind of thing you can deduce. Here's a slightly bigger example. I think I included this one because it's my favorite ever piece of artwork. So this is a distance regular graph on 102 vertices with valency 3, diameter 7. So there you see its intersection array. I won't invite you to confirm that just from the picture, but this is a particularly interesting example because it's a rare instance of a valency 3 distance regular graph with a primitive automorphism group. And in fact, there's only 3 examples of such graphs. There's a paper by Norman Biggs from the early 1970s called 3 Remarkable Graphs. And what makes them remarkable is that they are 3 regular and distance transitive, in fact. Okay, so distance regular graphs have been a bit of an obsession of mine for more than 20 years now, which makes me feel really old saying that. But it's a sufficient obsession that a few years ago I acquired the domain name distanceregular.org. And this is basically, it's a website which is a repository of distance regular graphs. Currently, there's about just over 200 in there. And for each graph in the database, there's a page with basic information, including the intersection array, including the eigenvalues and multiplicities. We have a picture of it, it's there. Links to other pages with information about the graph. Some graphs have Wikipedia articles, some have Wolfram Alpha pages. Andries Brouwer's website has several pages about individual graphs. But the main purpose of the site is to actually provide data files with computer constructions of the graph, which people can download and work with. And so here is a sample page, a completely non-randomly chosen example of a page. And you can see the information, there's a picture, and the top right there is where you can find the downloads. And so if you want to, say, do some calculations with examples of distance regular graphs, this is a place you can retrieve them from. So I know this is something that people have been finding useful over the past sort of 5 or 6 years since it was launched. But one thing I will say is that the collection of graphs in there there's a lot of people's favorites are in there, but it is also slightly haphazard. So one thing that is something I'm intending to do, which unfortunately the pandemic put the brakes on rather significantly, is make the collection a little more systematic, and particularly in regards to graphs coming from group actions, which has sort of always been my interest in these type of graphs. And so this is what we're going to learn about today, kind of what came out of this cataloging effort. Okay, so I'm interested in graphs which are constructed from permutation groups. So here's a little bit of background on that. So first off, a reminder, so if you have a group G acting on a set omega, this is transitive if for any two elements x and y, there is some group element that maps one to the other. Okay, so there's a single orbit on the set omega. And so, more specifically than that, now let's suppose we've got a group acting transitively, then a block system for the group is a partition of the set omega into equivalence classes for some relation preserved by this group action. So by which I mean x and y are related if and only if their images are related for under any element of the group. Okay, so this will split, the equivalence relation will split the set apart. Now, so there's two block systems which exist regardless of what the group is, and they're both kind of silly examples. So one is the partition into singletons. So we split the set up into subsets of size 1, and basically there's no relation possible, essentially. And so two elements related by being equal to each other. And so obviously this is going to be preserved by any group action on this set. The other silly one is the opposite extreme, where we have the universal relation where each pair of elements is related. There's a single equivalence class, so there's no structure left to preserve. And so this is technically, it satisfies the definition of a block system, and so it will be preserved by any group action on the set. So these two will always exist, but if these are the only block systems which exist, then we say that the group is primitive. Otherwise, if there is an interesting block system, then the group is imprimitive. So basically, a primitive group is one which preserves no equivalence relations other than these two silly ones. So that's the definition in terms of the action. But you can also phrase it in terms of the group as an abstract group. So if G is an abstract group and you know the subgroup structure, the primitive actions are basically the ones on the right cosets of maximal subgroups. So the maximal subgroup corresponds to the stabilizer of a point in the group action. So each maximal subgroup gives you point stabilizer. The group action is always equivalent to that on the right cosets of the point stabilizer. So knowing the maximal subgroups of a group is equivalent to knowing the primitive actions. So though this was phrased originally in terms of a group action, you can actually just phrase it in terms of the abstract group as well, if that's what you're more interested in. Okay. So what can a primitive group look like? Well, there's a theorem called the Onan-Scott theorem from around 1980, which there's different ways of stating the Onan-Scott theorem, but this is the version I'm going to go with. If you have a finite primitive group, it must have one of the following 5 types. So one is an affine type. So it's a group of affine transformations of a vector space over a finite field. So where you have all the translations are giving you a regular subgroup, translations by vectors in the vector space V, and then this extended by some subgroup of the group of linear transformations on V. And so here the action is on, we can identify the set which the group is acting on with that vector space V. Another case is the almost simple type. So if you have a finite simple group S, I should say a non-abelian finite simple group, just to be completely clear, because otherwise we'll be back in the affine case again. So you have a group G which contains your non-abelian simple group, but isn't much bigger than it. It lies somewhere between S and its automorphism group. And there's nothing in this definition about what the action is. It is just the action on some maximal subgroup of your group G, of your almost simple group. The third type is what's called product action type. So you take the two groups H and K. H is going to be almost simple. K is going to be some other group. And whatever size the set K is acting on, I'm going to take that many copies of H as the Cartesian, or that many copies of the set on which H is acting on, and the Cartesian product of that many copies of it. And then what H does is it acts as it would on each copy of its domain. And then you also have this group K, which is permuting the copies. So this is something you get on the Cartesian product of sets. Then there's two other types, which I'm not going to go into too much detail about, other than to say that they exist, and that in the type of analysis that this talk is about, they don't show up very frequently. So there's the diagonal type, and there's also a twisted wreath type. The smallest example of a group of twisted wreath type acts on 60 to the power 6 points. So if you were looking for a graph with that as its automorphism group, it would have 60 to the 6 vertices. So obviously this is not something that's going to show up computationally. Diagonal type, it shows up occasionally, and we'll see an example of that. But now to apply the Onan-Scott theorem, well, in the almost simple case, to apply that, you need to know what the finite simple groups are. And in the product action case, the group H has to be almost simple. Knowing the finite simple groups also comes into diagonal type as well, and I believe also into the twisted wreath type. So the fact that this appeared around 1980, which was when the classification of finite simple groups was announced, is not a coincidence, because you can't really do anything useful with the Onan-Scott theorem unless you know the classification of finite simple groups. But fortunately, we have that. And so putting this together, as well as Aschbacher's theorem from '84 on classifying maximal subgroups of linear groups, what various authors have been able to do is build catalogs of, sorry, there's a keyword primitive is missing, that should say all primitive permutation groups acting on a relatively small number of points. Now, some of this predates the Onan-Scott theorem. So a lot of this was done in the 19th or early 20th centuries for groups on up to 20 points. And then this was pushed up to groups on, or primitive groups on up to 50 points by Charles Sims, sort of in the early days of computational group theory in the late 1960s. But going beyond here, that's when the Onan-Scott theorem started to appear. So groups on under 1,000 points of non-affine type classified in the late 80s by Dixon and Mortimer. The affine ones appeared around 20 years ago. And then Ronnie Dougal was able to extend this a couple of years later onto groups on up to 2,500 points, or just one less than that. And then Ronnie Dougal again, along with Kautz and Quick, pushed this on to one less than 2 to the 12, so on up to 4,095 points. Now, recent work of a student of Derek Holt at Warwick University has extended this further. But what is important about these classifications is these are implemented as libraries in the main sort of computer algebra systems, GAP and MAGMA. So if you want to do any kind of testing primitive groups on up to 4,095 points for some property, then there are libraries available to do this. Now, there's also unofficial libraries floating around for going up to, I think, 1 under 2 to the 13, so on about 8,000 points now, but they're not sort of officially released yet. So I only really learned about those a week ago. So this cataloging effort continues, but these are the ones that are important in terms of what's actually available in the computer algebra. Sorry, I just noticed there's a bit of discussion in the chat there, but okay, so yes, a group is almost simple if it lies somewhere between a simple group and its automorphism group. And in fact, for this talk, most of the examples arise from that type of group. Okay, so there's this library. And so we can use groups to build graphs. Okay, so how can we do that? Well, let's suppose we've got a group with a transitive action on set omega. And so then the group acts on omega. Then you can also look at what it does to ordered pairs of elements from omega. So the Cartesian product of omega with itself. Okay, so the group is transitive, so it only has one orbit on omega, but then this, when you look at the ordered pairs, you can then potentially have many orbits, and these are what are called orbitals, orbits on pairs. And so in this context, the rank of the group, everyone's favorite overused mathematical term, the rank of the group is just the number of these orbitals. So you always have at least 2, because you can never map something of the form XX to something of the form XY, where X and Y are distinct. So you always have at least 2, but you could potentially have a lot more. One thing that's useful to understand is that the orbitals correspond directly with what are called the suborbits of the group, which is the orbits of the stabilizer of a point. So you take the subgroup of G, which fixes a point X, and then this will then break up the remaining, the subgroup will then act on the remaining points. You break that up. The orbits of that action correspond to the orbits on pairs. Okay, but because we have, as each orbit is a subset of the set of ordered pairs from omega, this defines a directed graph with omega as its vertex set, and each the set of arcs in your directed graph are precisely the pairs in that orbital. If you're lucky and the orbital's what's called a self-paired orbital, so XX is in it if and only if XY is, then you have an arc in each direction between X and Y, and so you've just got an undirected graph. If it's not self-paired, then the reverse orbital must also be one of your orbitals. And where these first arose was in work of Donald Higman in the late 1960s, which showed that a group action is primitive if and only if every orbital digraph apart from the diagonal one, which is a loop on each vertex, each of those is a connected graph. So on the one hand, we can define primitive groups in terms of equivalence relations, but we can also define it algebraically in terms of maximal subgroups, but you can also characterize it more combinatorially in terms of connected graphs. Okay, so So here's an example. So if you take the symmetric group acting on the two-element subsets of the set 1 up to n, then you have 3 orbits on pairs of subsets. You can have the sets are equal. You can have where they're not equal, but they overlap in a single point, so where the intersection is not empty, or they can be disjoint. So you have basically 3 cases, and because we have a full symmetric group here, each of these things is has just a single orbit on each type. And so here's that graph again. So in case 3, when n equals 5, you get the Peterson graph, a strongly regular graph with 10 vertices, valency 3, and lambda equals 0, mu equals 1. And so you can, the 10 vertices correspond to the 5 choose 2-element subsets, and which are adjacent when they're disjoint. And if you generalize this, or more actually, if you generalize the second case, if you take the action of the symmetric group on k-element subsets, and you make a graph where those are your vertices, you join them if they're adjacent in, or you join them if their intersection has size k-1. So this is an orbital graph of Sn in that action. Okay, and this is a family of distance regular graphs, the one that arises naturally from a very natural example of a group action. Okay, now one brief interlude here. So our aim here is to start building distance regular graphs. Brief interlude is just to mention what is meant by the word primitive. So you may have heard the term primitive in the context of distance regular graphs before. So if we just forget about groups for a second, a distance regular graph of diameter d is said to be primitive if each of the distance I graphs is connected. So the distance 1 graph is the original graph. The distance 2 graph has the same vertices, but 2 are adjacent if they had distance 2 in the original. And so you can get one of these for each distance from 1 up to d. And so we can define a graph to be primitive if each of these are connected. So these two notions coincide exactly when the graph is distance transitive. Because if a graph is distance transitive, the orbital graphs of its automorphism group are precisely the distance I graphs of the graph gamma. And then so the group is primitive if and only if all the orbital graphs are connected. The graph is primitive if and only if the distance I graphs are connected. Okay, so it is possible for a primitive distance regular graph to have an automorphism group which is imprimitive. So depending on the structure of the graph, then its distance I graphs may all be connected, but there may still be some equivalence relation which is preserved by the group action, particularly if the group is sort of relatively small. But the reverse is not true. So if you have a distance regular graph which is primitive, then because of the Higman criterion and the orbital graphs all being connected, this forces it to be a primitive graph. So such examples won't arise in the analysis I'm going to talk about. But there is a nice characterization of the imprimitive distance regular graphs. So an imprimitive distance regular graph is either bipartite or antipodal, which occurs when the distance d graphs are a connection of disjoint cliques. Okay, so If we're looking from primitive permutation groups, neither of those things will ever arise. Okay, so I just thought I'd mention that because sometimes there is a bit of confusion between these two meanings of the same word. Okay, so how can we make distance regular or strongly regular graphs? Well, if you have a graph which is vertex transitive, so automorphism group is transitive on vertices, then for any transitive subgroup of the automorphism group, the set of edges of the graph must be a union of orbitals or pairs of orbitals of the group G. So basically, any way of forming a vertex transitive graph from a group G involves putting together orbital graphs in some way. And so if you're using the GAP computer algebra system, the GRAPE package by Len Seutzer includes this nice function, vertex transitive DRGs. And what that does is if you feed into it a transitive group, and what it will do is it will tell you which combinations of orbitals of that group will give you a graph which is distance regular, or if the diameter is too strongly regular. And basically all this does is it looks at every single way of possibly combining orbitals or pairs of orbitals. So provided the number of orbitals, the rank, is relatively small, this will give you an answer in a reasonable amount of time. And so what I had my students doing was basically take the libraries of primitive groups in GAP and systematically apply this function and basically turn over a rock and see what lies underneath. And so what was the strategy? Okay, so for a given pair of inputs n and r, what we'll do is go to the group library, find the groups on n points with rank equal to r. Then go through that group and find which parameter sets for distance regular or strongly regular graphs show up. Make those graphs, and if it happens that the full automorphism group of the graph is bigger than this group G, we'll throw that away because we'll know, if we haven't seen it already, we will see it when we consider that larger group, which will also be in the library somewhere. Potentially, you can have multiple copies of the same graph coming from different combinations of orbitals of the same group. So what we'll do is we'll just reject any isomorphic copies. In the case where the group is of affine type, you get a lot of stuff coming out and it's difficult to make sense of it. But for the other types, and in the libraries, most of the examples which are not affine are of almost simple type. What comes out is much more manageable to comprehend. And most of the things you find are graphs which are already known. Many of which fall into infinite families. So the Johnson graphs that I already mentioned, coming from the symmetric group acting on K subsets, you'll find each of those. You also find, so coming from groups of product action type, which what you get primarily are the Hamming graphs, which are basically you take the vertices are the Cartesian product of D copies of a set of size Q, so D tuples over an alphabet of size Q, adjacent if they differ in a single entry. And so we get those, provided the number of vertices Q to the D is sort of within that range we're looking at. You also get Grassmann graphs, which are like Johnson graphs, but rather than made from subsets of a set, they're made from subspaces of a vector space over a finite field of order Q. More generally than that, or maybe not more generally, but related to that, rather than taking all of the subspaces, you just take those which are maximal totally isotropic subspaces in some polar space, and then so these arise from the classical groups. So for each polar space you have a classical group, and the action of that classical group on subspaces gives you something called a dual polar graph, and these also arise in this setting. If staying with finite geometries, if you have something like a projected plane or a generalized polygon, you look at the graph on the flags, so the incident point line pairs, and in many cases these come from some action of a primitive group. And so these are another collection of families that you will observe. This is not an exhaustive list. You get various other families, many of which are in Brouwer and van Melderham's book on strongly regular graphs, many in Brouwer and Cohen and Neumeyer's book on distance regular graphs. So every so often you'll come across an instance of one of these families. But perhaps, depending on your personal biases, what may be more interesting are some of the sporadic examples which don't really fall into any family. So from an unusual action of a group, or maybe from one of the sporadic finite simple groups. So we get things like the Hoffman-Singleton graph on 50 vertices, the Big Smith graph, which I showed you earlier, the one with diameter 7 on 102 vertices. That comes from the group PSL 217. From the sporadic finite simple group, so for instance, you get from the first Yanko group, you get something called the Livingston graph, which has diameter 4 and 266 vertices. The largest sporadic example that we found going up to 4,095 vertices is from another sporadic simple group, the Rudvalis group, and that has 4,060 vertices. There are also situations where technically it does belong to an infinite family, but it's so sparse that only one instance arises in this range of values. So this is the one example from a group of diagonal type. What you do is you take a non-abelian simple group, write out its multiplication table. This gives you a Latin square, and then you can make the Latin square graph from that, where you join two entries in the table if they're in the same row, same column, or have the same symbol in them. So the size of the Cayley table is the square of the order of the group. The smallest example is A5 of order 60, so the smallest example has 3,600 vertices. Okay, so this is an infinite family, but it's the only example that we see. So many of these sporadic examples were well known, but there were some surprises which showed up. So I'm going to talk a little bit about those now. So one is an example of a graph on 120 vertices. So we found 3 strongly regular graphs on 120 vertices, valency 63, lambda equals 30, mu equals 36. So there are millions of strongly regular graphs with those parameters, but only 3 of them arise from the action of a primitive permutation group. Okay, and 2 of these are well understood, one of which is something called a non-isotropic orthogonal graph. So what you do is you take the 8-dimensional vector space over a field of order 2. You take one of the 2 quadratic forms on that vector space, the plus type form, and just take those points which are non-isotropic with respect to that form, so where the form is non-zero. This gives you a subset of that vector space, and what we're going to do is join 2 of those points if they are orthogonal to each other. And this gives an example of an infinite family that arises from orthogonal groups. It has rank 3. So this is a well-known graph. It's described in Brown van Melderham's book. Another one arises if you take the Johnson graph J10-3, so 3 element subsets of a 10 set, and if you join those if they overlap in a single point, so 3 subsets adjacent if they overlap in a set of size 1. This is something which you can do for any JN3, but it's unusual for it to actually be distance regular itself. But this is one of the examples where it's known to happen. But the third arose from an action of the symmetric group S7 with rank 7. And so there's a line in the tables of Brown and van Mulderham's book, which indicates that they observed that this graph existed, but there's no information about how to construct it or how it arises. But you get a hint from where to look, because if you look at this rank 7 action of S7, you find this unusual graph, but you also find this non-isotropic orthogonal graph in there. So we can think of this mystery rank 7 graph as having the same set of vertices as this non-isotropic orthogonal graph. And then, so this gives you a place to start looking. And so last fall, when I was out in Brussels for just over a week, we looked at this with Sam Adriansen and Jan de Boele and Morgan Rogers, who was also visiting the same week. And so I will not do this construction justice by attempting to explain it in the time that I have. But suffice to say, there is a way of constructing this graph starting from the same geometry, from the non-isotropic points of this quadratic form. And it's sort of, the construction involves looking at the whole vector space and which points are in the polar space, the isotropic points, and which ones are not. And so it's an interesting piece of finite geometry constructing this graph. We also, moving on a bit further, looking at 136 vertices, we found 2 graphs with valency 63 on that number of vertices. So the first one of these is if you take the other quadratic form on the same space as the previous slide, you get a non-isotropic orthogonal graph from that. But the other arises somewhat strangely from an action of PSL 217 with rank 12. And this graph appears to be new. So the only place I found one reference to this graph in the literature, but where it was mistakenly believed to be the other graph, NO-82. So this graph had not really been investigated before at all. It doesn't appear in the tables in Brown and van Mulderham's book because they only go up to rank 10. Now, there's an infinite family of actions of these linear groups PSL2Q, PGL2Q, acting on Q choose 2 points. But for the range of values that we were able to test these groups, because the number of points is sort of large relative to the order of the group, you end up with or rather the group is sort of relatively small for the number of points, you end up where the rank grows as Q grows. So after a while, the computer runs out of steam. And while this is an infinite family of actions, it's only when Q equals 17 does a graph like this arise. And that's kind of weird. And also, we don't have that nice hint of where to look this time because you don't get the known graph as a union of orbitals of this group. So you don't get this sort of place to start looking like you did before. A possible interpretation is to look at another group on the same number of points, which does have PSL 217 as a subgroup. That's a symplectic group. So maybe there's some kind of geometric interpretation arising from this symplectic polar space, but if there is, I don't know what it is. Okay, so there's a challenge for you there. So these actions of linear groups. So the natural place this acts are on the q+1 points of the projective line, so the elements of the field plus a point at infinity. And these actions are what's called two homogeneous, which means that the group acts transitively on two element subsets of the projective line. So these groups naturally preserve the Johnson graph and the complement, the Kneser graph, in this situation. But in a couple of instances, like PGL27, you get the Coxeter graph, which has diameter 4 and 28 vertices. And there's another one coming from a generalized quadrangle from PGL29. But those are the only ones we could find, other than the Johnson and Kneser graphs, which you expect to find. So one question is there anything else? So recently I've been thinking about this with Dan Horton here in Rijeka, and the case of PGL2Q, then, and if we want the graph to be strongly regular, to have diameter 2, then Johnson and Kneser are the only ones that come out. But we still don't know what happens if you want something of larger diameter, and we still don't know what happens if you move down to the projective special linear group PSL2Q. And also, like we saw on the previous slide, there are actions not on q+1 choose 2 on the pairs from the projective line, but q choose 2 points. The geometric interpretations here are not as nice. But like I say, q = 17 is the only case where something arises. So there's another mystery waiting to be solved. Is PSL217 the only case where you get a graph from this action? Something else that has also been subject of sort of recent, been thinking about recently. So what happens when we have a group of affine type? So I mentioned that you get a lot of graphs coming from this situation, and it's difficult to kind of make sense of what's going on. But there are a few cases where the dimension of the vector space is small, where we can say a bit more. So if you have a graph with a group of affine type acting on it, you must have a regular subgroup, sort of isomorphic to the additive group of the vector space, acting as automorphisms. So you have this elementary abelian P group as a regular subgroup of your automorphism group. So basically, any graph that comes up from an affine group is going to have to be a Cayley graph of that elementary abelian P group. Okay, so first of all, the smallest case, if V is a one-dimensional space, so what we've got here is just the field, the only graphs that come out are, other than cycles and complete graphs, are going to be the Paley graphs, and you get those when P is 1 mod 4. And this, it's known exactly what the distance regular Cayley graphs of cyclic groups are. This was done by Miklevich and Potocznik about 20 years ago. And in the case of a cyclic group of prime order, then most of the examples don't arise, and Paley graphs are basically what you're left with. Now, when the exponent is 2 or larger, what you can do is show that the diameter of graph is at most that exponent. And Basically, this arises because you have this elementary abelian group, and then it has a Schur ring. The structure of a Schur ring can be associated with any Cayley graph of that, and then you can kind of go from there. And so when the exponent is 2, we're just looking for strongly regular Cayley graphs of this elementary abelian P group of exponent 2. And these, again, using this result of VLAN, can be described quite neatly. Basically, the connection set of such a Cayley graph ends up having to be, so if you look at the neighbors of the 0 element of the group, the connection set must be a union of the points of lines through the origin. So you take a subset of the lines in this plane, you take the non-zero points on each line, and that gives you the possible connection sets. These in turn correspond to the lines in the plane correspond to the standard construction of mutually orthogonal Latin squares from the field of order P. So you don't just get graphs with Latin square parameters, they really are Latin square graphs, and they are the Latin square graphs that come from the standard construction moles of order P. What's not obvious is when these graphs have primitive automorphism groups, because maybe you get, depending on how you choose the lines, there may or may not be some equivalence class. What's also not obvious is what happens when the exponent is 3 or larger. Maybe exponent 3 could be worked with, but exponent 4 or higher is probably just an incomprehensible mess. And very last thing I want to talk about also is this all began as a computer search, but there's still some computations that we were unable to complete. And the reason being is that the computations work well when the rank is reasonably small, but if you have a lot of orbitals, there's just too many of them to test every single combination. And so what we can do, though, is we think a bit more cleverly about it. We can say, well, we know, say, for a particular number of vertices, what the possible parameter sets of a strongly regular or distance regular graph are. Like stuff coming from eigenvalues, for instance, can be used to reduce this significantly. So rather than looking at every single possible combination of orbitals, let's just look at combinations which will give a particular valency. And so if we do that, we can reduce the search space quite a lot. So for example, PGL 227 has an action on 819 points with rank 43. So you can't possibly test all combinations of orbital graphs, even if we pair off the non-self-paired ones. But if we're looking for a particular valency, so
Robert, can you wrap it up?
Yes, it's my last slide. Yeah, it's my last slide. Okay, so there's a valency 400 slide, valency 400 parameter sets. So we can narrow this down. You can also split it into subcases to run it in parallel. Unfortunately, no graph showed up. And some even bigger searches, sort of looking for sort of quite large ranks on over 1,000 vertices. It would have been really nice if something had come out of these, because these parameter sets, certainly the 1015, there is no known strongly regular graph from any construction with that parameter set. Sadly, there wasn't one which came from a primitive group. But there's still a few left, some of which are probably way too big to even to deal with via this approach. But I will thank you for your attention and hope to see some of you in Rijeka in July.
Okay, thank you for the talk. Okay, any question for Robert?
Well, I have a question. So, yeah, so did you say the only SRGs with the parameters 120, 33, etc. come from your construction? Are just the only those three, no more? Potentially?
There are lots of others, because you can do switching operations on graphs with those parameters, and so then Ferdinand Iringer has a catalog of millions with those parameters, but of those millions, only 3 of them come from a primitive permutation group.
Okay, and so that's for sure, right? Mm-hmm. Yeah. Okay, thank you. Mm-hmm.
Okay, so any other question for Robert?
Yes, I also have a small question. So, Robert, in one of your slides, you mentioned that the projective groups coming from the projective line also act on Q choose 2 elements. And
Yes.
for Q odd, I can see this happening as working on the internal points of a conic. But for Q even, I was wondering if there's a nice geometric interpretation as well.
Pass. That's the kind of question I would be asking you.
Okay. But so, do you know whether it's also true for Q even, or?
Well, when Q is even, you still get an action. That there aren't any. None of the examples I've tried have any graphs that are coming from them, but then the only one that has graphs coming from it is 17. Or
yeah,
I think there's a smaller one where I think Q equals 11. Maybe you get one, but it turns out to be a Johnson graph.